Thank you, Andreas, for the very nice introduction. And thank you, everyone, for being here. I know it is almost Christmas time. If you are here, that means you're very dedicated in learning something new. So hopefully this talk will serve the purpose. So it's a great pleasure to present our work on studying the interactions and conformational flexibility of the antibodies using small angle scattering. This is some work that I get the chance to work with during my postdoc at NIST. All right, so, oops. All right, okay, so I guess this, because of the session, the name of this seminar series is Antibodies in Solution. I guess you guys don't really need this introduction on what monoclonal antibodies are. And, they currently constitute one of the biggest selling biotherapeutic products in the market. And then around the first 10 antibody approved by the FDA, majority of them are used for cancer therapy. All right. So when it comes to formulating the antibody products, there's a big drive for the pharmaceutical companies to formulate them for subcutaneous injections because it is convenient for the patients. And then, that can also avoid the production of medical waste if the patient has to visit the hospital every now and then for IV infusion. So imagine that. So for subcutaneous injections, the antibodies will be packed into an injection device. So for example, like an injection pen. So imagine that you're holding a pen, right? And it's a very small volume. So that means for the injection device, it can only hold a certain amount of volume, typically below 2 milliliters. So with that being said, the antibodies needs to be prepared at high concentrations, so typically above 50 milligrams per ml in order to achieve a particular therapeutic dosage. Okay, so for anyone who's working with proteins, we all know that with increased protein concentration, there's increased non-specific protein-protein interactions. And then such interactions sometimes can be troublesome. It can lead to aggregation or high viscosity of the antibody products, which are non-desired for subcutaneous formulations. So in this case, the antibody product sometimes needs to be formulated in a way to maximize their stability and to reduce their viscosity. So the formulation screening process can be a very time-consuming and labor-intensive process. So in order to determine the best formulation condition for a mAb candidate, there are several ways to do it. The first is the long-term stability testing. This is essential for ensuring the shelf life and efficacy of the mAb product. But, because of long-term stability testing, so it can be time-consuming and can be very labor-intensive because there are so many combinations of the formulation for combinations of the excipients that can be used to formulate this mAb product. And at the beginning, at the early stage of the development, people just may not have enough material to play with anyways. So then the other approach to determine what is the best formulation for a mAb product would be the short-term biophysical characterization methods. So in this way, the antibodies are formulated in a particular condition, like a formulation conditions. And then you can measure the antibodies through a certain technique. And then the experimental parameter will be correlated with the stability or viscosity of the formulation, of the mAb formulation. So you can correlate these experimental parameters with their long-term stability or viscosity profiles, and then to predict how well they could behave in such formulation conditions. So that you can use this method and can be high throughput as well. So this will significantly shorten the timeline that's used to determine what is the best formulation condition for a particular mAb product. So when it comes to characterization methods, there are many commonly used techniques, but typically for these techniques, they have a certain concentration limits. Okay, and as a contrary to all these techniques shown here, small angle X-ray and neutron scattering can be used to measure a wide range of protein concentrations from just a few milligrams per mil all the way up to hundreds of milligrams per mil. Okay, so that's why we are interested in using small angle X-ray and neutron scattering to study antibodies in solution. All right, so you may have already know about small angle X-ray neutron scattering, also known as SAXS or SANS. But I just want to quickly, talk about it in case if you need some recap. So the intensity coming from the scattering is related to these 5 different parameters. So the P of Q is what we know as the form factor. It shows it's related to the size and shape of the scattering objects. So if you have a different size or shape of the scattering or different size or shape of the protein molecules, you will end up with having a different look of the scattering profile. Structure factor is known as the S of Q term, and then it is related to the relative position and spatial correlation of scattering objects. So if you have a structure profile looking something like this, where towards the low Q, there is the S of 0 value goes beyond 1. That means you have net attractive interactions. If you have a structure factor profile looks like this, where the S of 0 value goes below 1 towards the low Q region, that means you have net repulsive interactions. And then if the structure factor, after you have done all the possible subtractions, and it looks something like this, like a flat line, that means there's either no interaction between the scattering objects or the attractions or repulsions are canceling each other out. All right, so that is for structure factors. So it depends on what they look like. You can tell roughly what is the nature of the net protein-protein interactions present in between your protein samples. Additionally, you can also fit the structure factor profile. Okay, so the most basic model that we ever use to fit the structure factor profile is the hard sphere model that considers only the excluded volume effect. Any additional interactions beyond the excluded volume effect will lead to a different fitting model. All right, so for example, this is a structure factor profile where we measured from NISTmAb prepared in sucrose solution at a protein concentration of 130 mg per ml. And we can see that the structure, the hard sphere model cannot be used to fit the data. Okay, the S of 0 value from the hard sphere derived from the hard sphere model is greater than that measured from the experiment. So in this case, like additional repulsive interactions are present between the protein molecules. In this case, we use the Hayter-Penfold model to account for such repulsive interaction. And then here's another example where we measured NISTmAb in perchlorate solution. And then we can see the S of 0 value derived from the hard sphere is greater than that derived, measured from the experiment. So in this case, we use 2U-Pavel model, which considers additional repulsive and attractive interactions in addition to excluded volume effects. So in a nutshell, by fitting the, the structure factor profiles using different models, you can have some ideas on what are the different, various energetic components that collectively contribute to the net protein-protein interaction. All right, so with that being said, let me introduce the objective of this study. So the objective of this study is to investigate the conformation and the protein-protein interactions of the mAb molecules under the near-neutral and acidic conditions. So near-neutral condition is important because some of the mAb molecules are often formulated in near-neutral, slightly acidic conditions. And then the acidic condition is also important because, during the purification process, the antibodies sometimes will experience acidic conditions, for example, pH 3, okay, during the protein A purification process. And then for this study, we have a special focus to characterize the roles played by different domains, so either the Fabs or the FCs, like how their interactions could, affect the behavior of the full monoclonal antibody themselves. So the model system that we use for this study, not surprisingly, is the NIST antibody reference material, RM8671, also known as NISTmAb. I'm very fortunate to get my hands on this material because yesterday I was checking the price for NISTmAb, and I'm surprised to see that the price has gone up from $1,200 a few years ago, all the way up to $700, where you can see it from Sigma Aldrich. So I'm very grateful for that. So the approach that we took for this study, we performed small angle X-ray scattering experiments and coupled with dynamic and static light scattering, as well as circular dichroism and FTIR spectroscopy to probe the secondary and tertiary structure change of the antibodies in different buffering conditions. And then as for the buffer conditions, we choose pH 3 as a representative of the acidic conditions and pH 6 for the near-neutral conditions. And the ionic strength has been changed all the way from 5 millimolar to 300 millimolar. So to cover this wide ionic strength. All right, so before I get on to my results, I want to briefly talk about how I prepared the NISTmAb fragments. So you may have your own protocols of doing this, and then you may have used this Fab preparation kit. But for me, because I want to prepare both the Fabs and as well as the FCs at large quantity, this is not a very practical solution for me because I am one of those frugal person. So for $750 that you pay for this kit, you can only digest 40 milligrams of NISTmAb tops. And then this have $750 already after discount. So that's why I decided to develop my own method. So to make the NISTmAb fragments, I choose to use papain, okay, because I want to have both the Fabs as well as the FCs, okay? So as shown in this graph here, pepsin, which is another commonly used protease, is not an ideal solution. So here is the digestion buffer conditions. You can find the details on how I did this preparation, how I did the fragmentation preparation in this paper right here. But one thing that I want to point out is that what I have realized during the process is that agitation or air-water interface should be strictly avoided, okay? If you are a trained chemist like me, you may have the habit of using beakers and stirring bars where you want to mix things together. And that turns out to be a terrible mistake. So I realized that during the digestion process, if you use beakers and stirring bars, I can see white flux starts to show up during the digestion process. So in the end, you have a lot of the white flux floating on the surface of the water. And then you can take a guess on what these white flux are. Apparently something aggregated. I will let you know what aggregated in the end of my talk. But to mitigate this problem, you should use so my solution is to fill the mixtures in a falcon tube. Depends on how you call them, what you call them. So 15 or 50 milliliter centrifuge tubes as well. So you should fill them like to almost fully, okay, to avoid as much air gap as possible. Parafilm them and then put them onto a nutator for gentle rotation. So by using this method, I have avoided the formation of the white flux. All right, so after digestion, you run the mixtures through the ICC column that can separate the full mAb, which is non-digested, away from the Fabs and FC mixtures. So this SCC chromatogram has been shows the digestion process after 2 hours of the digestion, which is pretty fast at 37 degrees Celsius. So the undigested mAb can then be collected and then used for another round of digestion. And this mixture of the FABs and FCs will then separate it by the protein A column. So to check the digestion process as well as the purity of the samples that I use reduced and denatured SDS page. So the flow through of the protein A column is your Fab fragments. And then the elution from the protein A column is your FC fragments. So in the end, the yield of the Fab is around 70%, and the yield of the FC domain is around 60 to 65%, which I think is pretty good. All right, so now I finally get the chance to talk about the results. So first of all, we performed static and dynamic light scattering experiments to measure the apparent molecular weight, as well as the protein diameter of NISTmAb prepared in different buffering conditions. So I show in this figure right here, we can see that for pH 6, the samples are prepared using 2 different kinds of buffering salts. And the same goes for pH 3, 2 different types of buffering conditions, well, 2 different kinds of buffering salts. But at pH 6, no matter what kind of buffering system that you use, the apparent molecular weight of the NISTmAb remains constant around 150 kilodaltons, suggesting that antibodies are monomeric across the examined ionic strength conditions at pH 6. So at pH 3, from ionic strength of 5 millimolar to 100 millimolar, the molecular weight measured from NISTmAb remains quite similar to that measured from pH 6, also at 150 kilodaltons. But as soon as ionic strength increased to 300 millimolar, there's a significant increase in the molecular weight that's measured from the NISTmAb, suggesting the formation of the high molecular weight species, okay, presumably, due to the self-association of the NISTmAb molecules. So now, then we look at the size of the antibodies measured at different conditions. So at pH 6, the diameter of the antibody remains constant across all the examined ionic strength conditions, around 10.5 or 10.6 nanometers throughout. However, as soon as the pH drops to pH 3, the size of the antibody increased, okay, and then shows that at pH 3, the antibody have a size around 12 nanometers. But we know from the molecular weight measurement that the proteins are monomeric. So such change in size, but constant molecular weight suggests that at low ionic strength at pH 3, the proteins are monomeric, but they have adopted an extended conformation. As soon as ionic strength increased to 300 millimolar, the size of the protein further increased, okay? And then this result is in line with the molecular weight results, both suggesting the formation of high molecular weight species. So next, at pH 3, we have seen the antibodies have some anomalous behavior. So at low ionic strength, they are all extended. At high ionic strength, they seem to aggregate. So to identify the underlying cause of this behavior of NISTmAb in acidic conditions at pH 3, we performed static and dynamic light scattering experiments on the Fab fragments only. So here shows the molecular weight as well as the size of the fragments measured at pH 3 across all the ionic strength conditions, going from 5 millimolar to 300 millimolar. And we can see that the size and molecular weight of the 5 fragments remains pretty constant across all the ionic strength conditions. There's no sudden jump in either the size or the molecular weight at 300 millimolar ionic strength. So at this point, we can hypothesize or imagine that the observed formation of high molecular weight species may have something to do with the FC domain. So Next, we measured the zeta potential of the full map as well as its fragments so that we can better understand their, because charge plays a key role in determining the conformation as well as the interactions of the protein molecules. So that's what we have measured. So we measured two different ionic strength conditions, one at 30 millimolar, the other one at 300 millimolar. So we can see that compared to 30 millimolar case, the charge that's measured from the whole map as well as its fragments shows a decreased apparent charge, which is not surprising considering that, this is, charge screening effect. And then by looking at these, then the trend shows for from these two figures suggests that, when the pH goes from 7 down to pH 3, the protein become more positively charged. Okay, and then because, the theoretical isoelectric point of NISTmAb and its fragments are calculated to be around pH 8. So as the pH goes away from the isoelectric point, the protein gets more charged. Okay, so that's what we have measured for zeta potential, and we can always refer back to the charge carried by the protein, by the full map and its fragments later on when we try to explain other results. All right, so now next we also performed CD and FTIR experiments to look at the secondary and tertiary structure change of NISTmAb when they are prepared at pH 3 or pH 6, both at low and high ionic strength. So by looking at the, the far UV, near UV, CD spectra, as well as the FTIR spectra, we can see that, the shape of this spectra look very similar to each other. That's measured from different conditions, suggesting that the antibodies themselves don't really have a very significant structure change. It's not like something is it's not like the protein is partially unfolded or completely unfolded. So, but if we look at the fine details of the spectra, we can see that these results are suggesting that at low pH, at pH 3, and high ionic strength, in this case 300 millimolar, the beta strand content decreased with a concomitant increase in the random coil structures. And this is in line with the light scattering experiments results, where we have found that antibodies form the high molecular weight species. Okay, so such secondary structure change may have something to do with the formation of these higher order structures. All right, so now, after talking about, the light scattering and CD-FTIR results, we finally get down to SAXS measurements. So we performed SAXS measurements on 2 milligrams per ml of NISTmAb prepared at pH 6 first to look at their structures. Because, SAXS depends on how you analyze the results. You can either look at the structure of the scattering objects, or you can look at the interactions between them. So at 2 milligrams per ml, that's considered as a low concentration. So at this concentration, we are only measuring the structure of the NISTmAb molecules. So this is the scattering profiles we measured from the NISTmAb prepared at pH 6 at various ionic strength conditions. And then the first thing that we do is to perform this PR distribution analysis, okay? And then for this PR distribution analysis, we see that the shape of this P of R curves look very similar to each other at different ionic strength conditions. They all feature two peaks. The first peak is always constant at around 40 nanometers. That's what we call the intra-domain peak. That is related to the size of the Fab and FC domains. And then there's another peak at around 80 nanometers. The peak position of this, peak doesn't change, but the intensity fluctuates, depends on which ionic strength you prepare your sample at. And then this peak, we think that's what we call the interdomain peak. It tells you the average distance between the Fab and then the FC domains. So this is what we have measured at pH 6. And then we also measured the NISTmAb here at pH 3. And then we do the same thing to do, perform the PR distribution analysis for the scattering profile. And then we see that at pH 3, at ionic strengths of 5 and 30, there are also two peaks, okay, shown by these circles and squares. And then the intradomain peak in this case has reduced slightly to 35 nanometers, suggesting the size of the Fab and FC domain slightly smaller as compared to that's measured from pH 6. And then the interdomain peak is shifted towards a lower, it's shifted towards a lower radius, lower distance, as the ionic strength increased from 5 to 30 millimolar, okay, suggesting that the distance between the Fab FC domain is reduced, probably due to the charge screening, okay? And then, however, as the ionic strength increased to 300 millimolar, the intradomain peak disappeared. And then we can see that the Dmax significantly increased, suggesting the formation of high molecular weight species, which is in line with the results we have collected from light scattering, as well as the CD and FTIR results. All right, so that's what we have learned from the PR distribution analysis. But in order to understand or represent the flexibility of the antibody molecules, we also went on to plot, to generate the density plots. So the density plots in this case were generated for the SAXS profiles measured at low ionic strength at two different pH conditions, so pH 3 and pH 6. The density plot is a representation of the volumetric space occupied by atoms in an ensemble of structures, and is derived by comparing theoretical scattering curves to the experimental SAXS data. You will know what they look like, after I go through the different steps on how they can be generated. So the density plots has been generated. So everything that you can do it using SAXS-Web. So the first step is to generate an ensemble of structures. So to generate ensemble of structures, we keep the FC domain constant, like we don't change the position of the FC domains, but we let the Fab domains to rotate, like they are freely movable. So here shows 3 representative structures, but for this experiment, I have generated definitely more than these 3 structures. There's like 65,000 of structures that I generated, so that the antibody conformation can be represented as much as possible. So next, after you have generated this ensemble of structures, then you calculate, so for each one of them, you calculate theoretical scattering profiles. So here shows only 4 scattering profiles, and in reality, I have 65,000 scattering profiles that I have, so that they can be compared with the experimental data using chi-square. Okay, so the underlying assumption here is that if a theoretical scattering curve give you a chi-square value that's less than 5, that should suggest that the experimental data is, that suggests that the theoretical scattering curve is like a good fit of the scattering of the experimental data. And it's likely that the antibody that you are measuring will have that particular conformation. All right. And then after you have compared all these 65,000 of scattering profiles with the experimental data, you should have a list of the antibody configurations that shows good agreement with the experimental data. And then that's where we start to plot, and that's where we start to generate the density plot. So at pH 6, and this meshed network represents the freedom of movement of these Fab domains. So means that the Fabs can be in different combinations but they all within this mesh networks. And then the antibody adopt these structures will generate a scattering curve that is in good agreement with experimental data. So as we can see, like the Fabs can have many, can have great flexibility. mAb can, adopt many configurations, but still like, fits experimental data. It's pretty much means that pH 6, you have a greater flexibility of the Fab regions. However, this is in contrary with what we have got for pH 3 conditions. So at pH 3, the Fab domains can only rotate in certain ways. And then the density plot we generated for pH 3, the Fab regions can only, rotate around this region or that region. That means at pH 3, your antibody have an increased rigidity, meaning reduced flexibility. And then from the zeta potential measurements, we know at pH 3 and low ionic strength, the antibodies are heavily charged. So it could be that these, the high charge coming from the domains could limit the flexibility of this Fab, could limit the flexibility of the antibodies. All right, so that concludes what we have done in terms of, studying the structure of the antibodies. Now we have moved down to looking at the interactions between them. So when you want to measure protein-protein interactions, there are the most commonly used methods will be light scattering. Okay, so from the light scattering, if you do static light scattering, you can get BT2 values. And if you do dynamic light scattering, you can get the KD values. And then both of them can tell you something about the interprotein interactions. So the cutoff values that suggest that either you have a net repulsive or net attractive interactions for KD will be 0. And for BT2 is 0. And for KD, we use -8. So by looking at these two graphs, so this graph on the left shows the KD and BT2 values measured from pH 6 across a wide range of ionic strengths. And then the figure on the right shows these two values measured at pH 3. We can see that with increasing ionic strength, both KD and BT2 values at both pH conditions is reduced, suggesting that the interactions between the protein molecules become less repulsive. And if you look at the exact numbers of the KD and BT2 value, we know that the NISTmAb shows net attractive interactions only under acidic and high salt conditions. So this is a condition where both the KD and BT2 values are below the cutoff value, suggesting that the overall protein content or overall protein interactions are attractive. So this is what we have got from the light scattering experiments. Now, if you remember what I have talked about earlier in my talk, that we can also use small angle scattering to look at the structure factor, and that can tell us something about interprotein interactions too. So from the scattering curve, you can derive the effective structure factor profiles by using this equation. And then I'm missing a scaling factor S here that corrects for the concentration. So here shows the structure factor profile we measured from pH 6 at low and high ionic strength and pH 3 at low ionic strength, okay? And based on the look of this scattering or structure factor profiles, we know that overall protein-protein interactions are repulsive in nature because they all deviate away from 1. But, we can also move on and then fit the structure factor profiles. And then that's why I have generated this plot right here. So the S of 0 experiments divided by the S of 0 derived from Hasphere model, this structure factor ratio can tell you something about which model that you are using to fit the data. So in this figure, each one of these dots represents a particular sample that I have measured. So each dot represents a particular concentration. And then generally with the increasing concentration, there is this structure factor ratio become further away from 1, okay? However, at pH 6 with low ionic strength, even though that the structure factor ratio is going to be further away from 1 with increasing concentration, these ratios are all collectively below 1, suggesting that the structure factor profiles were fitted using the Hater-Penfield model to account for additional electrostatic repulsions. And then, because they are all fitted using the same model, we can conclude that the crowding with increasing concentration doesn't seem to affect the nature of protein-protein interactions. Similar goes for samples that's prepared at pH 3, as also at low ionic strength, because this is a condition where the antibodies are heavily charged. So electrostatic interactions definitely dominate the protein-protein interactions. And then they can all be fitted using a Hater-Penfield model. Crowding doesn't affect the nature of protein-protein interactions. However, at pH 6 with high ionic strength, that's where this structure factor ratios starts to show dependence on the protein concentration. So at lower protein concentrations, they can be fitted using a 2-Yukawa model. And as you increase the protein concentration, the repulsion starts to dominate on the protein-protein interactions. So that shows that at pH 6, but increased ionic strength, the crowding does have some effect on the nature of protein-protein interactions. So what we have learned so far is at pH 3, at 5 millimolar salt conditions, the proteins are heavily charged, and then they show strong repulsive protein-protein interactions. But at 300 millimolar ionic conditions, as you can remember probably from the previous P of R distribution analysis, at as low as 2 milligrams per mil of the NISTmAb, there is a extended Dmax that we have got from the P of R distribution analysis, suggesting the formation of high molecular weight species that are formed. So in order to better understand what drives such formation of higher order structures, we look at the interactions between the Fabs and the FC domains. So here shows so in this curve that shows the Fab that's measured at pH 3 at the ionic strength of 5 millimolar. So we can see that the Fab starts to show repulsive interactions at 13 milligrams per mil. And then in this curve that shows the scattering profiles measured from the FC, we can see that for the FC domains, they start to show repulsive interactions at concentration at 6 milligrams per mil. So based on the scattering profiles we measured from the Fabs and the FCs, we can say that at ionic strengths of 5 millimolar, both the Fab and the FC domain contribute to the strong repulsions in the full mAb. So what happens to the 300 millimolar ionic strength case then? We measured the Fab, okay, and then the Fab doesn't seem to have any interactions, even the concentration is as high as 13 milligrams per mil. However, for the FC domain at pH 3 but high ionic strength, as soon as the concentration increased to 2 milligrams per mil, we can see the FCs are forming aggregates, so they self-associate at a concentration as low as 2 mg per mil. And then the NISTmAb shows that they form high molecular weight species already at 2 milligrams per mil as well at pH 3 and high ionic strength. So that's why we think the mAb self-association is probably primarily due to the FC attractions. All right, so what we have learned so far. So we have learned that at pH 6, across all the ionic strength conditions, NISTmAb remains monomeric and they are flexible, and there's no significant structural changes that's observed. And then the net protein-protein interactions are dominated by repulsions, despite that they are pretty weak in charge. That's measured from the zeta potential measurements. So what we can conclude from these experimental findings is that, the high flexibility could possibly allow the mAbs to adopt conformations that maximize the electrostatic repulsions. And then at pH 3, but low ionic strength, we know that they are rigid. They have adopted this extended conformation. And then there is no significant structural changes. And then the high charge could potentially lead to such strong repulsive protein-protein interactions. And then what we can conclude from here is that, both the FC and the FAB domains contribute to repulsive protein-protein interactions due to the high charge. And then finally, at pH 3, but high ionic stress conditions, we have observed the formation of high molecular weight species due to the self-association with the NISTmAb molecules. And then there is a minor secondary structure change that the beta strands unfolds into random coils. And then at pH 3, but high ionic strength, the antibodies are low charge due to due to salt screening. So it's possible that the self-association of NISTmAb was mainly driven by the FC domain, presumably through the FC and FC attractions, although we cannot rule out the possibility of the FC and FAB interactions, but we need to do more experiments on that. So now I can finally tell you what these white flocks are at the, if you remember from the beginning, when I mentioned about the fragmentation process. The white flocks appear to be the FC domains. So from here, we know the FCs are prone to aggregation. And then, the white flocks that I have observed earlier with when the protein is in contact with the interface, they are formed by the FC domains, probably because they're just so aggregation prone, okay? And then that's confirmed by the SDS page. And then finally, I want to highlight that combining SAXS or small angle scattering in general with other biophysical methods is a very powerful tool that can tell us many informations about mAbs in solution in general. So if we talk about conformation, we can do CD measurements, FTIR measurements, but SAXS provides additional information on what the antibody may look like in solution and tells us something about the conformational flexibility as well. And when it comes to protein-protein interactions, we can always do DLS and SLS, but we can also perform SAXS measurements as well because it is a high concentration measurement. You can measure the interactions of the antibodies at high concentrations directly, and that can break down the overall protein-protein interactions into its various components. So with that, I'd like to thank my previous my mentor, Joseph Curtis. He's the PI of this project. And then my collaborators at NIST and IBBR, and of course, LSU Department of Chemistry for hiring me as assistant professor where I can continue working on antibodies in solution. So with that, I'd like to thank you and I welcome any questions you have.